Hi, welcome to College Physics. This is the course where we study and introduce physics, and I'll be your guide through this tour, Ross Burrows. And what will we be learning? Well, we'll be learning the theories and methods and ways of measuring that lay truly at the heart of science, because that's what physics really is. It's about what you can measure and how you can use those measurements to analyze and understand in a scientific way the entire universe, from the microscopic to the macroscopic to the ginormous. Physics covers it all. So get ready to really dig in and really try to enjoy yourself as we introduce this wondrous and wonderful topic of physics. Here's the textbook we'll be using, College Physics by OpenStax. It's perfectly free, available for you online in both PDF and HTML formats. And if you just pick with the read online format, it has very nice embedded video content there for you. I personally like this book the most because it's, well, like I said, it's free. There's other college physics textbooks that are quite good, but none of them I know are as free and open as OpenStax. So that's the one we'll be using. And again, here's me, your guide through this introduction to college physics. And we're going to start right off at the beginning, talking about physical quantities and units, and mentioning just a little bit about what is physics and where can we use it. Well, what is physics is the heart of science. Physics is all about what you can measure and what you can show, and theories you can derive that you can prove based on measurements, what you can show repeatably. And where do the laws of physics apply? Well, as far as we know, they apply everywhere. They give us a scientific basis to study all observable phenomenon you can think of. From gigantic, like this Andromeda galaxy, which is something like 150,000 light years across. It's ginormously huge. To the Earth-Moon system, so putting astronauts on the moon, that was a project that fully featured physics. Without scientists understanding the basic laws of physics, fundamental Newtonian mechanics, and electrodynamics, there would be no man on the moon landing. Just could not have happened. And the scales between the Earth and the Moon, well, I would say they're microscopic compared to the scale of the Andromeda galaxy. And yet again, just to double down on what I said, without the laws of physics, going to the Moon would be just as impossible as it is currently to get to the Andromeda galaxy, thousands of light years away. There's no way to get there. So as small as the Earth-Moon system is by comparison to the Andromeda galaxy, so is too a system, say, of phytoplankton here on Earth, where these phytoplankton could be on the order of a micrometer, say 10 to the minus 6 meters, up to millimeters, which is 10 to the minus 3 meters. So the laws of physics that we're getting ready to unfold and learn are applicable to all of these realms across ginormous different orders of magnitude of scalings, from ginormous to huge to incredibly small. And here's some faces of physics, and somehow I managed to get my face in over here on the bottom right. And if you think your face should be in here, we support you in that. If you have the enthusiasm and you start to enjoy this subject, just keep going as far as you can and make your contribution, and maybe you can join the ranks of these very important faces of science and physics, the forefathers, if you will, that have paved the way for us to understand so much that we can in the scientific way. So again, how are we going to go about this? Well, we're going to go about it by learning to understand what we can measure. So we've seen some faces of science, and maybe there should be more diversity in science than there is. And hey, if you want to see your face in there, we definitely support you. Put the work in. If you enjoy science, do as much as you can and make your contribution. Get your face in there. And when you get yourself in there, what are you going to be doing as a scientist? Well, what you'll be doing will crack down to reporting phenomenon or results of experiments or theories or what have you. You're going to report them in terms of something that you can measure repeatably, measure and verify. And what can you repeatably measure and verify? Well, the most fundamental things that you can measure and verify, three of them will be length, time, and mass, or mass, length, and time. So that's three things right here. What other things are there? Well, SI, System International, defines 7 basic quantities that you can measure that all other measurements will crack down to somehow, that the kernel fundamental quantities. And here we've only got 3 of them here. SI says there's 7 of them. So what are the 7? Well, I would submit to you, let's not worry about what they are right now other than length, mass, and time. And I would add one other one here, and I would submit that there's one other one we could add to here that would be quite fundamental, and that would be charge. And that would have units of coulombs. So in SI, the fundamental unit of charge is coulombs. All right, so we may want to ask, what is charge? We'll start over here at the top, actually, and say, what is length? Well, length is what you measure with a ruler, say a meter stick. But what do you have to even have a ruler, a meter stick, to measure length with? Well, even before you had the meter stick, you'd have to have mass, right? That meter stick is made up of mass. So I would say quite fundamental, even more fundamental than length, is mass. And what is mass? Mass is what you measure with its force interaction with another mass. You kind of know what it is in a sense that you have mass. It almost seems awkward to ask the question, what is mass? Since you are a massive body, you have the sense of what it is. So saying, oh, okay, well, what is it exactly? And then to find out that exactly what it is what you can measure as its force interaction with another mass. Seems a bit recursive, but that's just how it goes. And length is what you measure with a ruler. And time is what you measure with a clock. And so what does time tell you? Time, in a sense, tells you or gives you some description of how the mass is changing. And so mass changes if it's changing its state. Well, I'll put it to you like this. Suppose nothing were to move. Everything was just stuck in one spot. The mass went nowhere. Then what would the meaning of time be anyway? For time to have any meaning, then things would have to change from one moment to the next. And what gets changed? Well, the mass. And the charge. And what is the charge? Somehow the charge is embedded in the mass. So charge is a property of protons and electrons, or fundamental particles. They have this property of charge. And how do we measure charge? We measure charge by its force interaction with other charge. So charge is what we measure with other charge. A charge has the property mass, or mass has the property charge. I'm not sure which. We could say fundamental particles have both these properties. They have the property of mass and charge. And how do we measure those? Well, we measure them by their force interactions with each other. So if this all seems kind of recursive and you feel like we could have just checked off all these boxes and just say, these are the things we're going to measure, length, time, mass, and charge, and they're defined by how they're measured, we probably could have just went, check, it's all well and good. Even to talk about it and to try to think, oh, okay, what is it that we're thinking about? What are we talking about? Almost brings confusion to the topic. And that is because these are such fundamental quantities. These are really the quantities that are at the bottom of the barrel. They're the nuts and bolts of the engine. And they're quantities in this sense that we have to take for granted, and we have to have these to define anything else. Everything is defined in terms of these. Language, you have to have mass, length, and time to make language, right? You saw me write out right here, I'm underlining charge, coulomb, and its units, C. That is mass, length, and time. Unfolding, the writing of these letters, mass, length, and time, unfolding. And you're listening to the sound of my voice, or you're looking at this lecture. These are properties of mass, length, time, and charge unfolding that you're literally measuring with your eyes and your ears. So literally you have to be able to measure these fundamental quantities in some sense and define them as how they're measured before you can define anything else, before you can have language or art or even science. Okay, so we're going to talk about these things, and when we specify a quantity, like for example, I may specify some amount of charge, like 5 coulombs. Okay, let's say, my charge equals to 5 coulombs. Notice I had to put the unit here, coulombs, for what I was talking about to make sense. Right? I couldn't just go charge. I couldn't say charge equals 5. That wouldn't make any sense at all. I needed to say 5 coulombs like I did over here. Or if I was talking about a length, so L is some length, and I can't tell you that length is 5. That doesn't make any sense. So let's say this is Bob right here, and Bob is wondering, how far do I have to go down to the trail here to get to the treasure chest where X marks a spot, right? You have treasure chest and a red X. So he wants to get to that treasure chest, and he wants to know how far he has to go down the trail. And so he needs an answer here. And if you tell him, okay, it's 5, he doesn't know what that means. You go, well, this is 5 cobble. 5 cobble. And he's like, I wonder how big a cobble is. And let's suppose cobble is not even a unit of length. Distances given in unknown units are useless. That's what the sentence says right here. Well, I guess that's true. If he says 5 cobble, and he doesn't even know what a cobble is, and that's useless. Just as useless would be to give no units. And ultimately, at the end of the day, he needs units that he can use, right? Like length is equal to 5 miles. Now, that's something he can use because he knows what a mile is. So for any physical quantity that you want to write down and specify, you definitely need to give its units. And that may seem a little bit pedantic or excessive and redundant to tell you that, but it turns out to be the case that when some students do a calculation, they've done so much number crunching that they didn't want to keep all their units in the calculation, and then they get the end of some calculation and all they have is a number, and then they'll report an answer to you just with that number. Like they might say, okay, so the mass M is equal to 2.75, and then they don't tell you what that number is. It's 22.75. They don't tell you that it's kilograms, or maybe they don't even know if it's kilograms or maybe grams. It could be kilograms or grams. Anyway, if you just reported a number here, M is equal to 22.75, no one really knows what that is. It's a meaningless number if it's to represent some kind of a physical quantity, one of these, and especially one of these basic physical quantities, and the quantities that we will derive from them. And by the way, for this class, these 3 right here are the ones we're going to use almost exclusively for the first part of this class when we cover the topic of mechanics. All of the higher level units that we'll be using, like units of force and units of power, units of energy, all those kind of units are going to crack down when you break them down to their fundamental kernel units. Fundamental kernel quantities are going to break down into these 3 fundamentals: mass, length, and time. So these are SI units for mass, length, and time, which is the main units we're going to be focusing on for the study of mechanics. And we also mentioned that there's charge. We could have thrown in charge as our force unit, and I would have submitted to you that in some sense completes our list of all the things you can measure, while SI, they tell us that there's 7 fundamental quantities we can measure. And if we look at what those quantities are, we would see charge wasn't even one of them. So I said, they would say, okay, yeah, mass, length, and time. Those are definitely, it's the fundamental quantities. And then they don't even have charge. What do they have charge in? And actually in SI, they define the unit of amperes, and that's current, so that's charge per time. So they define amps equal to the charge per time, which would be coulombs per second. But anyhow, don't need to worry about that so much. We're just going to be concerning ourselves with mass, length, and time for the first part of this course, 12 chapters or so. And these are the SI units for those quantities. There could be other units you could use. So we might want to say, oh, we're going to measure length in some other units. And if I put this box around something like this set of brackets, what I mean is just grab the units. Grab the units, man. For length in SI, we'd have units of meters. Okay, so that's SI, but let's say we wanted to use some other units. Instead of meters, we wanted to use feet. I want to measure something in feet. That's fine. You can use whatever units you want, but if you want to now go to SI from there, what do you have to be able to do? You have to be able to state the relationship between the units you want to use, like feet, and the units of SI. I happen to remember that there's 2.54 centimeters is equal to 1 inch. 2.54 centimeters is equal to 1 inch. I also know 12 inches is equal to a foot. Okay, and what I've wrote down here, these things are what they call conversion factors. If it was up to me, I'd prefer to call them dimensional relationships or unit relationships that tell you what the relationship is between one set of units and another set of units. But here we see why we call them conversion factors. Let's say we wanted to use units of feet and someone told us, okay, length that we're talking about is 5 feet. But since we're going to also be using SI units as scientists, we want to use SI. I would also might want to know what that length was in meters. So what is that in meters? So this is probably a review for you, but definitely we want to know how to be able to convert between different sets of units. So for this particular case, what could we do? One thing we could do is use these conversion factors. So how do you set up these conversion factors? Well, I like to do what I call make a magic one out of them. So here I got this 5 feet, and so I want to be converting this into meters. I have this conversion here between centimeters and inches, and actually centimeters, that actually stands for this centa right here in centimeters. That C right there actually stands for 10 to the minus 2. So if I wanted just to straightforward convert it to meters, I could actually just move the decimal place twice on here. And we'll just do it in 2 steps. I'll convert to centimeters and then go from centimeters to meters. It's pretty straightforward because I could do another conversion factor here. 100 or 10 to the 2 centimeters is equal to a meter. Okay, and if I put the C standing for 10 to the minus 2, if I were to substitute that in right here, then I would have 10 to the 2 times 10 to the minus 2. 10 to the 2 times 10 to the minus 2 is actually just 1. Those two things would just knock each other out, and you'd be left with meters equal meters. But anyhow, let's just go on with our conversion here. We're going to go ahead and convert this. I'm going to make myself a magic 1. First, I'm going to get it into inches. So I made my conversion factor right here. If I divide both sides of this equation, so if I go foot divided by foot and 12 inches divided by foot, whatever I do to one side of an equation, I do to the other, then anything divided by itself is 1. And so what I've then done here is made what I call a magic 1. This thing here, this 12 inch over 1 foot, is the magic 1 right here. That's a magic 1. And why is it magic? Well, feet's going to cancel with feet, and I'm going to be left with inches. Okay, and then from inches, I want to go to centimeters, right? I'm trying to get to meters. So I go to centimeters, I'm going to be quite in the running there just to get to meters. So I'm going to use this next conversion factor. 2.54 centimeters is an inch. And then the last step, since we want to get to meters, I'll make a magic 1 out of this conversion factor. You can see I'm just following the same pattern. If you wanted, you could flip these upside down. So what I'm telling you is that from over here, since both of these are equal to 1, then a foot divided by 12 inches would also be equal to 1, or 10 to the 2 centimeters or 100 centimeters divided by 1 meter would also be equal to 1. So you can invert 1 and you still have 1. So those would still be magic 1s. The trick is you want to pick the magic 1 such that you can cancel off the units in the numerator and denominator, and at the end of the day you come out with the units you were looking for. So let's just start from the left over here. So I got feet cancels with feet. So this feet cancels with this feet. This inches cancels with this inches. This centimeter cancels with this centimeter. And the last unit standing, meter. So all this stuff is going to work out into units of meters. Now it's a job for our calculator. And at the end of it all, we got L is equal to 1.524 meters when I plugged all this into my calculator. Now, something we could ask ourselves here is sig figs. How many sig figs should I report in this? Well, in an operation like this, technically if this is one sig fig here, so I gave my length 5 feet, that was only one sig fig, there should technically only be one sig fig in the answer. Now, do I follow that pattern for myself? Well, it's good to be able to know the rules of sig figs, and we'll discuss that a little bit in an upcoming video. But for now, we could just note that for general homework purposes and for general purposes when I'm reporting an answer, what I use is I don't worry about sig figs, but just don't report so many that I feel embarrassed by the answer. So in this particular case, I feel really good about reporting the answer as 1.5 meters. L is equal to 5 feet, which is equal to 1.5 meters. Even though there's only one sig fig up here, and I got two sig figs down here, I would rather not round this up and report that as L is equal to 2 meters. I think almost for obvious reasons. I feel better about reporting it like that. So properly, if we're really staying true to our sig figs, we should report it like this, L equal 2 meters. But I do not mind at all reporting it like this, L equals 1.5 meters. On the other hand, this 1.524 meters is a bit embarrassing when we consider we just started off with one sig fig over here, and now how do we get all this precision over here? Nobody knows. So if you reported it like this, I probably wouldn't take any points off, but this one I feel like is pretty good. So we talked about length, and talked about these SI units, and in SI, the units for mass, length, and time are what we show here: meters, seconds, kilograms. So if you want to report something in SI units, then everything about that quantity that you're reporting should crack down to these units: length in meters, time in seconds, mass in kilograms. And now let's think about how these units are defined. Okay, so well, how's a meter defined? Well, the most basic way to define a meter for me is just to go, okay, I got a meter stick. Okay, so here's a meter stick, and I define a meter to be the length of that meter stick. However, if you're the Bureau of Weights and Means, if you're a scientist at SI, Bureau of Weights and Means, is this how you're going to define the meter? From this wooden stick here, that's a meter stick, is that going to be a good definition of a meter? Turns out, no, you're not going to be satisfied with that definition of a meter. And they're going to go ahead and define a meter to be the distance light travels in this many seconds. 1 divided by this number of seconds here would be easier for me to report in scientific notation. To 1 sig fig, this amount of time is going to be easier for me to report this as, because there's a giant number here. Like I look at how many times I move the decimal place. 1, 2, 3, 4, 5, 6, 7, 8. And then to round it to 1 sig fig, 1 over 3 times 10 to the 8 seconds. So they're saying that a meter stick is the distance light travels in 1 divided by 3 times 10 to the 8 seconds. You may already know that speed is defined as how far you go, so the length you go over the time it takes to get there. So particular length, in this case, if I just solve for it, some particular length would be the speed that you go times the time that you go for that speed. And in this particular case here, the speed is the speed of light. And generally they report the speed of light as c. They give it this letter c times this time, and that's to be equal to 1 meter. So that means that the speed of light, if I look over here and say, okay, the time is going to be 1 over 3 times 10 to the 8 seconds, and then the speed of light is going to have to be 3 times 10 to the 8 meters per second, and then we're going to multiply that by 1 over 3 times 10 to the 8 seconds. The seconds is upstairs, actually. And we can see that's going to cancel with that. This will cancel with that. And this whole thing is 1 meter. We guess, well, why in the world would they want to define a meter that way? Well, it turns out the speed of light is a fundamental constant of nature. Speed of light in a vacuum is always going to be pretty much this number right here, c 3 times 10 to the 8. And here's just a 1 sig fig, meters per second. Actually, if I wanted it to more precision, I would write all these digits out. It would actually be, the speed of light would be 299,792,458 meters per second would be the speed of light. But you can see why I would prefer to write it this way. And by the way, this goes to show you the usefulness of scientific notation, right? It's actually easier to write 3 times 10 to the 8 meters per second than to write 3 and then 8 zeros. Okay, I find it's easier to use this one up top here, which got crossed out. So that shows you the usefulness of scientific notation. And it's even more useful when you're reporting even bigger numbers than that, like Avogadro's number. What's that? So that's Avogadro's number. That's the number of molecules per mole, or number of particles per mole. For this number, can you imagine, would you ever want to write this number out as this number with the decimal place here moved 23 times to the right? No, you would never want to do that. So scientific notation is something you should get comfortable with and learn how to use if you already haven't figured it out. It's not that bad. It's much better, in fact, than trying to write this number in full form. Okay, so what have we learned here? We've learned a little bit about scientific notation. We've learned that the meter is defined as how far light travels in this very short length of time. This many 1 over 3 times 10 to the 8 seconds, roughly, to 1 sig fig. And it's defined that way because light is a fundamental quantity of nature, or a fundamental constant of nature. That is, it's something that doesn't change from place to place, from time to time. It's constant all the time. And if you can define your units, your base units, in terms of fundamental constants of nature, then that's going to be basically the best you can do. You can imagine the problems, like if you try to define the length in some other way, like say as the length of this meter stick. Well, how do you know that this meter stick is always going to have the same length? I mean, how do you know when Bob was handling it, he didn't just shave a little off that end or add a little to that end? This meter stick is not a fundamental constant of nature, whereas the speed of light is. So if we can define our meter in terms of a fundamental constant, then we're going to be doing much better towards getting a consistent and accurate definition, which, as you can imagine, is what we want in science: consistency, accuracy, constancy. So we've defined length as the distance light travels in a short amount of time to get you 1 meter. Now, how are we going to go ahead and define time, or define the second? Well, probably back in the day, you would have defined the second in terms of the length of the day. Right? So length of a day, 24 hours a day, 60 minutes in an hour, 60 seconds in a minute, and so on, and define a second that way based on the length of the day. Here again, is the length of the day fundamental constant of nature? Not so much. But actually, the rotation of the Earth is slowing down just a little bit due to drag forces, and from what I understand, the day is shortening just a little bit over time. You can check me on that, but the length of the day is not a fundamental constant of nature. What is? Oscillation of cesium atoms? Yeah, it'll turn out that if you have a big batch of cesium atoms, which is mostly the batch that you're going to have, right? If you grab a hold of like a sample of cesium, say a handful of them, how many cesium atoms are going to be in that handful? On the order of Avogadro's number, which we just wrote down, was like 6.023 times 10 to the 23 and more atoms. And on average, overall, the oscillations of these cesium atoms are going to be turning out to be so constant you could set your clock by it. They literally set their clock by how many oscillations these cesium atoms make in 1 second. This many on average. You have a big sample of them. And that turns out to be quite constant, and I'm assuming that they pick cesium-133 for this because they have really regular oscillations. And so the second is actually defined now to be based on cesium oscillations. 1 second is equal to this many oscillations of cesium atoms on average in this atomic clock, which they're going to measure with an oscilloscope or something like that. Anyway, the scientists at SI have worked that out for us, And so now we have a very accurate definition for a fundamental quantity for time in the second.